Welcome to the ChemDoctor. This is the first video in the series on molecular geometry. And what I want to accomplish in this presentation is to first talk about the relationship between a simple Lewis formula that we see on a piece of paper and what we can't see when we look at the formula that we've drawn, which is that particular molecules have three-dimensional shapes, and one of the key things that chemists need to be able to do when they're sketching molecules is to be able to visualize the shape of the molecule. One of the main reasons for this is because in terms of the chemistry of molecules, their shape quite often determines what their reactivity is going to be, or at least it influences the types of chemical reactions that these things undergo. So it's very important when we draw a Lewis formula or a structural diagram that we're able to visualize when we look at that molecule what its three-dimensional shape is. Now, when you're learning about this in your classes, whether it's a high school chemistry class or a university level general chemistry class, oftentimes in these chapters, the way that they teach this is by giving you a list of tables where you have to count the unshared pairs of electrons and the bonding units, and then you memorize this correlated with the geometry. And I'm going to admit that I am old school, and I use a different method to do this that an organic chemist taught me a long time ago. And what I like about this method for being able to visualize the shape of a molecule is that number one, it's a lot easier once you know how to determine hybridization, which is going to be the main point of this video. Once you know how to determine hybridization for a molecule, you can infer the geometry from that using a few little tricks. The benefit is that there's way less to memorize, and a few simple rules that I'm going to introduce in the next two videos allow you to basically look at just about any molecule that's utilized in either general chemistry class, organic chemistry, or even biochemistry, and be able to determine the shape of a molecule around a central atom. So let's go ahead and get started. And like I said, the main point of this first video is going to be to teach you how to determine the hybridization around a central atom, because that's going to be the one thing that you need to be able to do in order to infer the shape. And then in the next video, what we're going to do is actually apply that and talk about different examples. So let's begin with the simple molecule methane. And then one last thing. In these two videos, it's absolutely mandatory that you know how to draw Lewis formulas. And on my website and on my YouTube channel, I have a huge number of videos that deals with this issue. So if you don't know how to if you don't know how to draw a Lewis formula, you really need to stop right now and go back and deal with that, because in this video we're not going to have the time to go through the rules for structure drawing and how to do that, and I'm basically going to have to bounce directly to the structures. So for methane, if we're going to draw the Lewis formula, okay, this is what it's going to look like. There's going to be 4 bonds to the carbon, and to the novice, it literally appears, number one, that this molecule is flat on the piece of paper, and that it's got 90-degree bond angles between the respective hydrogens, which is absolutely wrong. All right, now what I've done is, over here on the right, is I've actually provided a three-dimensional picture of what this molecule looks like, and you can see that it's not flat and that the bond angles indeed are not 90 degrees. All right, so this is methane. All right, so these guys here are the hydrogens. All right, and this guy in the middle is the carbon, and my bond angles here, for example, this bond angle going across here like that, is actually 109. 0.5, and the type of shape that's represented here is a molecule that is tetrahedral. All right. So the question is, how do we get from here, all right, to here? So when I see this molecule, the picture that I'm showing here is what I see in my brain, and that's the goal here. That's where you need to get. So how are we going to do that? How do we get from something that is a central atom with 4 other things bonded to it to this image that you have in your mind? All right. And what we're going to do to get to this point is utilize a concept called hybridization. And hybridization has to do with the following understanding. When we have atoms that are forming bonds, so we're going to have a carbon that's going to bond to 4 hydrogens. The way that they do this is they overlap their atomic orbitals, producing molecular orbitals. All right, and so think about what orbitals are available to these 2 atoms. They have both s and p orbitals. All right, and I'm gonna keep this simple. This is not a lesson on molecular orbital theory or literally to go very deep into the concept of hybridization. Other than what you need to understand is that in order for carbon to bond to hydrogen, they're going to have to overlap atomic orbitals. The atomic orbitals that these 2 elements have available to them are going to be s orbitals and p orbitals, and they're going to mix these orbitals in order to have a place to pair up the bonding electrons. So remember that in each of these covalent bonds, all right, you have a pair of electrons that are bonded up, all right, and they're existing in the space between the nuclear centers of the carbon and the hydrogen. So how are we going to relate the mixing that they're doing? Because this concept of hybridization is basically going to give us the arrangement of electron pairs around the central atom. And the electron pairs and how they're arranged will be of 2 types. The electron pairs will either be bonding electrons or unshared electrons. So let me go ahead and we'll define that really quick. So hybridization all right, this is the mixing of s and p orbitals to form molecular orbitals. Whoops. Molecular orbitals, which in essence are the binding. If you want to look at it this way, I think it's fine. The binding orbitals. It's the place where we're going to put the electrons. All right. And furthermore, and I'm going to abbreviate this, hybridization gives the arrangement of electron pairs around a central atom all right, and these electron pairs are of 2 types. All right, they're going to be bonding pairs and they're going to be unshared pairs. Okay, so let's get with the program now. So let's look at this particular molecule, and what we're going to do is determine its hybridization. So hybridization is going to be given by the following constant relationship. It will be sp raised to the x, where the s refers to the number of s orbitals, and the p refers to the number of p orbitals. Now, in terms of simple molecules, well, in terms of any of the molecules I know of, actually, there's always only going to be one s orbital that's involved in the mixing. So the business end of this comes down to determining how many p orbitals are actually going to be involved in the mixing to form the molecular orbitals. And remember, the whole point that we're doing, the whole point of this is having a way of very quickly being able to look at a molecule, determine the hybridization, and then here is the key to this. The hybridization is going to tell us, we're going to be able to infer directly, using a few tricks, exactly what the shape is. So the key becomes finding the X, because there's going to be different variations of this. We're going to have SP systems or SP central atoms. We're going to have SP2 central atoms. And we're going to have SP3 central atoms. All right, on the simplest level. So how do we find X? So here's what you're going to do. All right, you're going to add up. Let me just finding X. That's what we're doing here. So you're going to add up all the bonding units. I'll define that in a minute. We're going to add up all the bonding units and subtract 1. All right. Now, what is a bonding unit? All right, so I need to define that. And this is actually pretty easy. In fact, I think it's one of the easiest things about chemistry. There's not that much variation here at all. So a bonding unit is literally going to be a single bond. All right, it could be a double bond. It could be a triple bond. And it can be literally one pair of unshared electrons. All right. Now, the best thing to do is for us to literally go into a mode where we practice this. So we're going to do some molecules, and I think once you start the pattern, you'll see how this works. All right, so let's go to a really simple molecule, beryllium chloride, BeCl2. The Lewis formula for this is going to be the following. All right, make sure to put my electrons in. And like I said, it's really mandatory that you know how to draw Lewis formulas, because I don't have the time right now to take you through that. All right, so we end up with a molecule like this, and this happens to be one of the atoms in period 2 that violates the octet rule, and we see that it only has 4 electrons around it. Now, to find the hybridization of this molecule, literally what we're going to do is count the bonding units for the central atom and subtract 1. So we see that there's literally 1, 2 bonding units. We subtract 1. So this molecule, we say, is SP hybridized. All right, and it's going to turn out that SP molecules are linear. All right, so and I think I'll just write that down. They turn out to be linear. All right, so anything that comes up with SP hybridization is going to be linear. Now let's take a look at another possibility here. Something more complicated, like carbon dioxide. All right, if we look at its Lewis formula, this is it here. And again, what I want to know is the hybridization around my central atom. All right, so we're going to count 1 bonding unit, 2 bonding units. We subtract 1, and we get SP hybridization again. So this molecule is linear. All right, now let's turn to, let's add another atom into the game here. So instead of only having 2 things attached to the central atom, now we'll have 3. All right, and boron is another example of an atom which can violate the octet rule. So what we're going to have for this will be this Lewis formula, where the central atom only has 6 pairs of electrons around it. get these guys. Whoops. All right, let me put my electrons in to be accurate here. All right, and then we'll determine hybridization. And you can see that now we've got 3 bonding units here, so it's going to be 1, 2, 3. We subtract 1. So this molecule is, we say, sp2 hybridized. And it's going to have its own unique geometry, which happens to be trigonal planar. Whoops. Planar. All right. Now, let's go to the molecule that we started with, which is methane. CH4, and this, again, this central atom, remember the picture that we were looking at the beginning of this, will have 4 atoms around it, the central atom, and when we go to do the hybridization, it's going to be 1, 2, 3, 4, subtract 1, so my hybridization here is sp3. And sp3 hybridized systems are going to be tetrahedral. All right, and the bond angles are going to be 109.5. The trigonal planar is going to be 120, and our linear molecules are going to be 180. All right, and with that, I'm going to go ahead and close the video.